The first type of wave energy converter we will discuss is the point absorber. Point absorber wave energy converters are a variation on the classic navigational buoy. The image on the right shows a navigational buoy in San Diego Harbor, complete with a seal enjoying the sun. A navigational buoy is essentially a floating tank anchored to the seabed to keep it in place. It marks channel entrances for ships. Buoy color, lights, bells, horns, etc. help navigation in all kinds of weather. Wave energy converter point absorbers are typically larger. This navigational buoy is probably 3 meters in diameter. Point absorber wave energy converter devices differ in how mechanical energy is extracted from the buoy motion and converted to electric power. I will present two different point absorber designs as illustration. The first is no longer produced, but there is a good bit of information available from its development program. The Aqua buoy was developed from two earlier designs, both from Sweden, the IPS buoy and the hose pump. Aqua buoy is a point absorber design, a small point of contact riding the wave. It was developed by a company called Finnavera Renewables, which is located in Vancouver. The unit consists of 4 elements. So there's the buoy, essentially the tank that rides the waves. There is a tube attached, solid tube attached to the bottom, an acceleration tube as it's called. There's a piston, which is, so this tube is cut away in this illustration. It in fact is a circular tube. There's a piston here, and the two blue lines in here are special rubber hoses that constitute hose pumps. So let's talk about the Aqua buoy operation. Let's start with this simple diagram. So let's talk about the components first. So the acceleration tube is, as mentioned, this circular tube which is suspended beneath the buoy. And it has both ends open to seawater, so you can actually see some ports here in the illustration so that water can pass back and forth unimpeded. And then the piston is in the middle, which is a neutrally buoyant disc. And when the buoy is at rest at a neutral position, the piston is held in a balanced position by the tension of the two hose pumps, one here and one here, which at that point are in balance. So let's talk about how this actually operates then. So the hose pump in operation, it's a steel reinforced rubber hose, and the internal volume is reduced when the hose is stretched, thereby acting as a pump. So in this case, where the buoy has been raised by the passing of the wave, as you see here, essentially the water is forced out of this stretched part of the hose pump, so the piston moves relative to the tube. Actually, this thing all moves up relative to the piston. The water is forced from the tube into a turbine, which is right here, and then it goes back around to the bottom and into the hose pump on the bottom. There's also as the buoy rides back down the wave, the opposite situation occurs. The piston motion has to move up. It stretches the bottom hose, and so water is pumped then through here up to the turbine, and then it comes back into this section. So a key part of this operation are the two relatively check valves here, which allow for flow. Okay, this is the reason I presented information about Aqua buoy. There's actually some published performance data. So this plot shows the power output developed in kilowatt for various bins of significant wave height. So the column here, the first column, is the significant wave height, and this is the peak period. All right, so not the zero crossing period, not the energy period, but the peak period. It's the way the data is presented. So here are the period values. So these numbers here then represent the power outputs in kilowatts for the different combinations of P and H sub S. Now notice this particular unit is rated at 250 kilowatts maximum power, and so I've highlighted in red a number of points here, and the unit basically limits the power output to prevent damage to the generator. So in some of these places here, the potential in the waves might actually allow for higher power outputs, but the generator is limited to its maximum to prevent damage. So a power limiting feature. A couple of aquabuoy projects are listed here. There was none of these were actually ever constructed, but there was a proposed one in Washington State in the US, one in Canada at Ucluelet, BC, and the one I want to mention is in fact Humboldt County in California. There was a plan for a 2 megawatt demonstration plant, and indeed an application for feasibility was filed in November 2007. The reason I mention this particular one is because it's a really good illustration of the NIMBY problem, not in my backyard, from a wave energy perspective. So the context for this was the U.S. Federal Energy Regulatory Commission, FERC, issued a lot of permits across the United States for hydrokinetic power projects in the sort of 2000 to 2008 timeframe. So hydrokinetic would include not only waves but also hydroelectric, run-of-river hydro projects, tidal current flows, all sorts of things. And there was really no provision in this process for local consultation, and so local authorities and communities often found out about the project after the permits had already been issued. So just as a representative article, this is a headline from an article that appeared in the Christian Science Monitor. Wave power proposals alarm locals. In Fort Bragg, California, Mayor Doug Hammerstrom was surprised last year to find that waters off his town had been claimed by a major utility with a preliminary permit application. The city filed legal motions to participate in the permitting process. Okay, so the outcome of that was in October 2008, the California Public Utilities Commission denied approval to a Pacific Gas and Electric application to purchase power from the 2 megawatt Finnevera Renewables wave energy project in Humboldt County. So that was a project that was based around the aquabuoy design. So another good illustration of the idea that people don't like surprises, and it's important to involve local communities in the initial planning process. So as a result of that, and indeed the timing was horrible because 2008, 2009 was a financial crisis. Finnevera then essentially put all their aquabuoy activities on hold, and indeed then in 2010 sold the technology. Now unfortunately I've not found any evidence that the new owner of the technology has moved forward with it. So just to give you an example of a device that's available currently, this is the Mark III power buoy developed by Ocean Power Technologies, a US company with branches in the UK and Australia. So let me call your attention first of all to the dimensions. This is a big unit. If we look at the float diameter is 11 meters, so again thinking about the navigational buoy, which we're perhaps more familiar with, this is a lot bigger. The overall length is 43.5 meters, although only 11.5 meters is above the water line, but still that's a significant height, certainly house kind of height. And it's designed to be used in a minimum water depth of 55 meters. Obviously with an overall length of 43.5, you need some clearance on the bottom. There is a very nice video of the deployment of the power buoy for test at a location off the coast of Scotland, and that video is nice because it puts the size in context. You can see objects of known size, like people for example, in comparison to the power buoy. So let's talk a little bit about the power buoy operation. There are really relatively few components in principle. The machinery is all inside basically. But the main component is a long cylindrical tube called the spar, right? So this is the spar, so that has substantial length. And it's held stationary by a heave plate. So this is a large, heavy plate which is at the bottom of the spar. And the idea is that that plate is at a depth such that the wave motion doesn't cause much influence. So the function of the heave plate is basically to hold the spar steady in terms of its height. So then we have the float, and the wave motion as it goes by moves the float up and down relative to the spar. So think concentric tubes. You can think of the center of the float as moving up and down on the tube that is the spar. So there is a mechanism then to convert that float motion into action on hydraulic cylinders that are inside the spar, and the hydraulic cylinders then pressurize and pump hydraulic fluid. The hydraulic fluid drives a hydraulic motor coupled to a generator, and that produces electric power. So there is a video which illustrates the operation. All the machinery is really inside the spar, and so the video shows exactly how that's done. But for the purpose right now, this is all we need. So let's talk about a few specifications. It's designed for a wave height range 1 to 6 meters, and the buoy in fact locks in place on the spar for higher wave heights to prevent damage to the mechanism. There's a 3-point mooring system that keeps it in place, and the mooring system and structure have been certified by Lloyd's Register, which is important for any marine structure or ship or whatever to obtain insurance. It has a design life of 25 years. So the unit has 866 kilowatts peak generator rating, produces power from waves with heights as small as 1 meter, and in tests in the North Sea produced power of 45 kilowatts from wave heights of 2 meters. Right, so those are some information available from the data sheet for the unit. So the company that produces Power Buoy has some projects in development. So there's an agreement with Australian Renewable Energy Grant, which is still under development. That could go ahead if some additional funding is found. In Japan, OPT is working with Mitsui Engineering and Shipbuilding for prospective power buoy stations off the coast of Japan. There was some activity in Oregon, which is now on hold, and there's some contract work being done with the European Commission on advanced power takeoff and also on wave prediction models. So no really concrete projects right now, but certainly some activity. The company seems to be devoting resources right at this moment to a smaller unit that they make, an autonomous power buoy it's called, which is an instrumentation platform, much like a navigation buoy. And the instrumentation platform has a power system internally which produces 350 watts to power sensors, and has a battery system to as a backup power supply. In terms of utility scale power, still under development basically. So going back to point absorber wave energy converters in general, some interesting future developments have been proposed. This was a proposal from Oregon State University to couple a buoy with a linear induction generator, and so instead of requiring rotary motion as most generators do, a linear induction generator generates power by simply reciprocating motion of the armature. So in this design, there's a permanent magnet armature attached to the seabed, and so then the buoy, which contains a wire-wound stator, moves up and down on the armature with the wave motion. So you can see the oscillation there, and the mechanical motion then of the buoy on the armature is converted directly into varying frequency alternating current. So in principle, this is a lovely idea. It's a huge challenge for power electronics because of the varying frequency. But if this could be made to work at reasonable cost, it would be more efficient than converting the mechanical motion to hydraulic pressure and then using a hydraulic motor and a generator. It could conceptually at least be much simpler. So let's try to summarize a few things. I want to point out first of all that there are many very interesting point absorber devices available and underdeveloped. I mentioned the AquaBuoy because there's a lot of data available, including the performance data the power output data that I presented. And the other device, the PowerBuoy, is merely representative technology, but there are plenty of other companies out there with these types of devices. So relatively simple installation for point absorbers. You can tow to the site, and indeed there was an OPT video on how that's done. The modular nature of point absorbers enables phased development projects. So this is perhaps an advantage where there's a lot of financial risk involved in these demonstration projects, and so initial success can be followed by additional modules to get much more data. So like all wave energy technologies, long-term trials are needed in some revenue service to validate the long-term performance, the economics, and the survivability. There are no specific practice problems to do for this lecture, but it would be useful for you to search and see if you can find some other point absorber wave energy conversion devices.